All right, let's look at beats. All right, let's say you have two sine curves. Let's say sine of omega 1t and combined with another sine curve with different frequencies, say omega 2t, right? And what will be the resulting curve? All right, so I'm going to use the trig identity listed here. So sine of a plus b plus sine of a minus b is equal to 2 sine of a times cosine of b. All right, so what I'm going to do is I'm going to try to map, let's see, a plus b in this case corresponds to omega 1t, and a minus b corresponds to omega 2t. Alright, so let's set up an equation here. So we know that, let's see, a plus b, so set a plus b to be omega 1t. And a minus b to be omega 2t. Alright. Then if you add them up, we can get 2a, right? So add these two equations up. So you're going to get the 2a is equal to omega 1t plus omega 2t. So I'm going to write it as omega 1 plus omega 2t. So a can be found by simply divide through by 2. A is going to be equal to omega 1 plus omega 2 over 2t. Alright? And if you want b, we can just subtract the second equation from the first equation, and a's cancel out, and you're going to get the 2b is equal to omega 1 minus omega 2t. Then we can divide through by 2 to get the b to be omega 1 minus omega 2 over 2t. Alright, so we can write it this way here. So magnitude is going to be 2, right? And I'm going to actually write cosine first. And cosine of b, we found b here. So I'm going to have a cosine of b, which came out to be omega 1 minus omega 2 over 2t. And then you have sine of omega 1 plus omega 2 over 2t. Alright, then we can view this as this. You can think of this as going to be a sine curve with this this part is the changing altitude. Actually, not altitude, amplitude, sorry. Alright. So let's try to see if we can visualize this using GeoGebra here. So I'm going to open up a GeoGebra. Alright. So what we do is I'm going to combine two sine curves, right, with slightly different frequency. So for example, we can probably put so y is equal to sine of say maybe 21 x, right? And I'm going to combine that with another sine curve with a slightly different frequency. I'm going to put 20 x, right? If you hit enter, and you will see that we'll have a curve. So sort of like here's the cosine curve. If you follow this right here, this is going to be a cosine curve. All right, maybe I should draw that on it. Let's see, we can probably here. All right, so here, this is the cosine curve. All right, then you have a more frequent, sine curve is kind of enclosed inside. All right, and this is called beats. You can see that here, this would be 1 beat. So from here to there, you have 1 beat. All right, and we can actually hear this beat using the following experiment. So what we can do is I'm gonna open up a tone generator. All right, this is an online tone generator, and what I'm gonna do is I'm gonna give 2 sounds with slightly different frequency. All right, so here I'm gonna play a sound with 440 hertz. So it's gonna sound like this. All right, maybe that. All right, then I'm gonna open up another tone generator. All right, then I'm gonna give maybe I'm gonna give exactly the same frequency for now. All right, so it's gonna sound like this. All right, not much change, right? And what we're gonna do is I'm gonna change this frequency slightly. So I'm gonna give this one 1 hertz smaller. So the first one has a 1 hertz higher frequency than the second one, and you can hear the amplitude amplitude changing, large and smaller, large, small, large, small, right? And this is called beats. And if I change a little slightly more, then you see that the beats gets faster, and you can hear that, right? So I mean, this is another reason why this is called beats, so you can hear the beats. All right, and we can see that the frequency of this beat is actually just the difference between the frequencies. So for example, in this case, right, this is a 440 hertz, and the second one is 1 hertz smaller, so the difference is 1 hertz. So you have a beat every second, 1, 2, 3, 4. But if I reduce it to 338, you can see that you hear 2 beats in 1 second. All right, so let's go back to algebra here. All right, or actually I have to turn the sound off first. I'm gonna stop this one, and I'm gonna stop this one. All right, so let's try to find the frequency of the beats. Right, so the frequency of the beats is determined by this guy right here. Right, so that's the circular frequency of the cosine curve. Right, so let's find the frequency there. So remember that the frequency of the first one, F1, is equal to simply W1. Omega 1 is a circular frequency. Then you have to divide by 2 pi, because a cycle is period is 2 pi. And also F2 would be simply omega 2 over 2 pi. Right? So if you look at the frequency, F is going to be, so it's a omega 1 minus omega 2 over 2. Then you have to divide by 2 pi. Right? Which can be rewritten as, so I'm going to pull out the 1/2 here. Right? Then you have omega 1 over 2 pi and a minus omega 2 over 2 pi, right? So this is going to be simply 1/2 of the difference between f1 minus f2, right? So we have to be a little bit careful about this. If you look at the picture here, right, you can see that the frequency, or maybe I should look at the cycle of cosine is actually go up and down and up. So that's one cycle, right? The cycle for the beat is actually only a half of that, which makes the frequency twice as big, right? So if you want to find the beat frequency, right? So here is the beat frequency, right? Let's call it f sub b, right, for beats. It's going to be, right, twice as big as this frequency here. So it's going to be f1 minus f2. So this is just the frequency of the first sine curve and the frequency of the second one. And then since we don't want to deal with the negative number, so I'm going to just put the absolute value sign. Right? So that is the frequency of the beats when you combine two sine curves with frequency f1 and f2. Beat frequency is simply the absolute value of the difference between those two frequencies. Right? That's it. I hope that this was clear.